next presentation, this will be your Mische from University of Augsburg, Germany. Nice place, Augsburg. Whoever hasn't been there, I certainly recommend to visit it. It's not far from Munich. Very nice place. So Jörg received his diploma in engineering degree in computer science from University of Augsburg, and he worked on hard real-time simultaneous multi-threading, received PhD in computer science in 2011, and he is currently involved in the project Palm Merasa on hard real-time capable medical processes. So we're going to hear about things related to. Okay, so
no, this talk is not about.
Not real-time. Yeah.
No,
Okay.
It's the next step.
Yeah. Thank you.
So thank you. I will talk about the network on chip as an alternative router design, and in future we decide to connect to the real-time, but this is not our route. So this alternative router design is motivated because we want to use network on chip in the embedded space, where the cores or the processing elements are smaller, and so the routers should be smaller too, because to have a relation between the size of the router and the core. So the core is smaller, we have to use smaller routers, and this is the one possibility to make the router smaller. How will we do it? We reduce we want to reduce the area and the power consumption. We will do this by reducing complexity, but we try to provide an acceptable network throughput for embedded systems. So a small outline. First, I will introduce this router microarchitecture. Then I will explain the algorithm for the routing, and give some numbers on the throughput and the energy consumption. So I'll compare it to a conventional router. So I think you should know all of this. So typically you use a mesh with bidirectional links between the nodes. You have the node, you have this connection to the local processing element, this is the corner, and you have 4 bidirectional links, so 4 input and for output ports, or with the local ports you have 5. You have a crossbar between them. You use typically wormhole routing, therefore you need buffers at the inputs or at the outputs. It's not important, but typically you use it at the input. Then to improve the throughput and to avoid deadlocks, you use virtual channels. So you need for every port you need more than one buffer. And you need a lot of logic to control all of this. Typically this logic is pipeline because there are so much things to do with everything for forwarding a message through the route. Now, what are we doing different? The different thing is that we don't use a mesh, we use a torus, and not a bidirectional, only a unidirectional torus. So the difference is that you have here this wraparound links. So you only go in one direction. So if you want to go from this one to that one, you have to go once around the link. You don't have this shortcut. What is the difference to a mesh? So the bidirectional bandwidth is the same for both. So just have this cut here. So the bidirectional bandwidth is the same. So it's a measure for the throughput. So this is equal. The number of ports per node is smaller in a torus, but the link length is longer because you have to add this wraparound, and so the link length is about the double. But you have half the links, so the link area is about the same. But the capacity, so the number of messages that could be, or the flits that could be within the network is half, so this is worse than the mesh. One problem for the clock frequency is this long wraparound link. So, but you can do this by rearranging the net and just, it's called then folded, and so you have here always links that are all double the size and in a mesh, but they have all the same length. So to avoid this wraparound. So what do we do on each browser? Here you have the conventional, and now we reduce it. So you have only got one input and one output. Add 2 inputs, 2 outputs. So this reduces this ports. Then, as we have only 3 ports, so the crossbar is reduced to 3 times 3. And we use a different routing, which called semi-bufferless. It's not completely bufferless, but it uses a lot less buffers than a conventional router. So there's only 1 buffer per router. And since all things are simpler, you need a much simpler arbitration logic and flow control, so the logic is becoming much less true. So now I'll go how the things work. So this torus, you can see them as a number of rings. So you have horizontal rings and you have vertical rings, and they are connected. And they are constantly rotating. So you put a message here in, and then it rotates, and they just go around. So you have vertically horizontal moving rings, and you have vertically rotating rings, like this. And then you put your messages in these rings to transport them. So here's an example. So we have here this node, and we have here message. So it comes from the processing element. There is an injection of things, and now it has to wait for a free slot in this ring. So here's the free slot. And now it just has to wait until it arrests. So then the message is put into the ring, and then it's transported on the x direction as long as it reaches its x destination. Then here, when it's reached it, it's put in the buffer. This is why we need 1 buffer. The buffer at this, we call this corner buffer. And there it waits for the horizontal, for the vertical ring that there is a free slot and that it can enter, and then it is transported to the the destination. Call it paternoster routing because it's like, I don't know if you know the paternoster lift. This is an old kind of lift where you just end, it just goes around and you enter and can go to another. Now there are some conflicts that have to be dealt with. For example, if the corner buffer is full. This could happen. What we then do, we just give the flit that is in another round through this ring. So it's just takes 1 extra round. Another thing is if there is if a message from the ring, from the horizontal and from the vertical ring arrives at the same cycle, and both want to eject to the processing element over the local port, then we have priority to the horizontal ring and to the vertical ring, and the horizontal ring just takes an extra round, like in this case. And take the same logic for both cases. We don't need this extra round for vertical rings. And one problem is if you don't get, I showed you the example that you need a free slot in this ring. So, and the problem is what to do if you don't get one. So maybe here this one won't send it. If this constantly fills and has all, it has enough messages or flits, you can completely starve this node. What you can do, you just have here some backlinks. It's only just 1 link with 1 bit to demand a free slot from the preceding node. And when it gets this signal, it just uses only the free slots, only every other free slots that he gets. So if he gets 1 slot, he uses this, the next one he lets free, so then the next one can use it, and so on. And if this one does not get a free slot, it can even demand the one before him, and so on. So this is a cascade to ask for a free slot. Another thing that is simplified is the flow control. We use only single flits, so we don't have packets like in a conventional router. We have only single flits. But as the flit order is preserved through the network, we don't need a package. We just send multiple flits behind each other, and we don't need a package header or a package tail. This simplifies the flow control, but we have to preserve the flit order. This is, as we use XY routing, that's not very difficult. The only problem is when you take these extra rounds. When some buffer is full, there you have some special logic that the flits still have the same order. The details are in the paper. And you have some overhead, because now every flit has to be added a destination node. But this is not so much. You just have to go the right X and Y direction. So you add a few bits, and in return you save the head flit of a packet. So then you have about a package size of about 4. So 4 is the border between. So if you have 4 or less, the overhead of per flit is less, and if you have longer packets, then it's better to have a head flit. But yeah, so this is the point. So it's not that bad. What I forgot on this slide is the deadlock. You don't have any deadlocks because you have only flits. This is so you have this reduces the problems when one packet is on 2 nodes and blocks 2 nodes. This is one. And the other point about deadlock is that it's avoided because you have this XY routing. So the X is completely independent of the Y routing, and so you cannot have a deadlock. Now I come to the evaluation. We compared it to a conventional router with 2 virtual channels and 2 buffers per input. And this was by Buxom from William Daly. We used it, and for the power we used Orion 2.9 at 65 nanometers. So you saw a lot of these diagrams today. Here, this is the conventional, the baseline we compare with, and this is our paternoster router with different sizes. So here the number is always the size of the buffers per node. And as you can see, when you increase the number of the size of the buffer, you can increase the throughput. But this is the maximum. If you increase it more, you don't get any more. So it's slightly worse than this conventional router. This is for uniform random traffic. The other typical traffic look all about the same. So they are in the same range. Some are slightly better here, some are slightly better there. For example, tornado traffic. Here is the paternoster is better than the conventional router. This is nice because Tornado was originally designed just as worst case for torus topology, but for bidirectional torus. So when you see here what you do, if you have 4.4, you always send to this, because when you have bidirections, this is the maximum, the other one would be to go here around, and so in a bidirectional, this is the worst case, but not in a unidirectional. There is not the worst case. It's just somewhere in the middle. Here, the worst case is neighbor traffic, which for conventional is very easy. So, but here it depends where your neighbor is. In a mesh, it doesn't mind. So The neighbor is just a diagonal neighbor. So here, but in this unidirectional torus, you have a neighbor that is on the ideal position because you have just this connection here and here, and you have one in the very worst connect. This is the direct here on the other side. You have to go this ring completely and then this ring too. So this is the worst case, and you can also see this in the throughput latency. So here you have the conventional with, here, and there you have if this neighbor is optimal positioned, so you nearly get maximum throughput. But when it's on the other side, you get a very low and even varying the number of buffers, you don't get any more. You don't get any more throughput. So here this is only with one buffer. So you don't need the buffers because you just send them directly. Here are some numbers on the area. What you can see here, the arbitration logic and allocated for them. This is only a small number, so the really important things are the buffers and the crossbar. And this 3x3 buffer crossbar is much smaller than a 5x5 crossbar. To be exactly in the Paternoster, you don't need a 3x3, you only need 7 of these 9 connections. So it's even smaller. And you see only the buffers make some difference. The same is for energy. I don't show this here, but it's about the same numbers. Now you can combine it. So in this picture, I have the saturation throughput here on this line. So the more in this direction is good, it's better. And the energy consumption on the Y, so lower is better. And here you can see a conventional router without virtual channels, so with only one buffer. Here with 2, and here with 3. So what you can see, the energy consumption it's only small increase from point to point. So for the conventional routers here with 4 virtual channels, even you can increase even more the number. So if you really want to reach a high saturation throughput, you have to use the conventional router. But if you don't need such a high saturation throughput, then you can use the Paternoster router because its energy consumption is much lower than for the other architectures. So to sum up, I presented a semi-bufferless routing in a unidirectional torus. We save energy by omitting packets, flow control, and virtual channels. And it's good for low power when it provides low power consumption for low throughput. So for future work, we want to examine real workloads because that's the question. So for example, Splash or something like that. Do we need this high throughput of other conventional, or is it enough the low throughput we can provide with the Paternoster router? And we want to improve the power modeling because Orion has some problems with small structural sizes, and we want to compare them with other low power router architectures, and maybe we have to model this all in VHDL to really compare it to get real numbers that we can rely on. And as mentioned at the beginning, we want to change the algorithm to provide some guaranteed service for real-time applications. So, thank you. And here is a build of a Paternoster lift.
Oh, that's very nice.
Thank you.
Thank you very much. In computer science, we used to have about 20 years ago. They stopped it and they ordered it because they had one fatality.
Yeah,
it's very unsafe.
You have some historic, but you may not some new ones.
But very useful. I mean, if you can guarantee safety, I think it's really quite efficient method of transporting people. Well, questions, please. Yes, please.
You mentioned that the deadlock doesn't occur in this router design, but can you comment on protocol deadlock as opposed to routing deadlock?
On what?
Protocol level deadlock.
On protocol, so.
For example, if there is a request-reply pattern, traffic pattern, in the conventional router design, we need at least 2 message classes or 2 virtual channels to guarantee there's no deadlock. So, what can it happen in this network?
So if you have, I'm not sure. I think that's not because you have different paths from. So if you have different paths from and back, so you don't get uncertain.
Will it be guaranteed also by?
But no,
you said that the fleet order is important. Yeah?
The fleet order, yeah.
Fleet order is preserved. Maybe.
Yeah.
If fleet order is reversed, then maybe you're right. There might be some. But fleet order is preserved.
Yeah, that's conserved.
Yeah.
But I think you can still get protocol level deadlocks. Yeah, because you can fill up the whole network with requests, for example, and start the
yeah, then you cannot starve. You avoid the starvation. I think then you can avoid the starvation. So starvation is avoided. So if you
but starvation of a specific message type, I think you may need 2 networks to make this, to avoid protocol level deadlocks.
I have to think about that.
Yes.
Yeah.
I think Ray that's really good stuff. Yeah.
I think you need to, deal with the protocol because it could happen.
Okay.
That, this is deadlock free at the router level, network router, but not at protocol level.
Protocol level.
Yeah. Could be solved.
That's an interesting point. Thank you. Any more questions? Not. I think, basically that was related, because I was about to ask you questions, since everything is in the fleet, so the header is there. So I was wondering what's the point of preserving the order? But it looks like maybe order is important.
The order is if you send large packages. If you want to send large messages, if one could overtook the other one, you don't get.
Okay, so if there are no more questions, thank you very much, Georg.